Hello, welcome to our review lecture for the Intermediate Classical Mechanics course in 2023. I'm not sure I will have much to write, but I made a lecture notebook anyway, and let's see what we can do. First thing to remind you of, review your homework and the work examples that are also on YouTube. Now let's go through what we have been doing during the semester and just review what is important. Let's start from the beginning. Chapter 1, we talked about Newton's laws. Well, you have to be familiar with Newton's laws. There isn't much more than that to say. Remember law of inertia, the second Newton law. I don't know who Newton is, sorry. Newton's laws. Inertia is equal to mass times acceleration equal to time derivative of the linear momentum. And remember the distinction between inertial and non-inertial frames of reference. If the frame of reference is inertial, Newton's first law is automatically satisfied. That's the definition of what an inertial frame of reference is. If Newton's first law is not satisfied, the frame of reference is not inertial. As simple as that, and vice versa, of course. The third law is not necessarily always satisfied, especially in electromagnetic problems, but for the problems we're going to look at in classical mechanics, that works. So we're good with that. That means that the variation of momentum, if we have two masses acting on each other, F12 is going to be equal to F21 with a minus sign in front. So the forces are equal and opposite. And that's what the third law tells us. And if all internal forces are acting on a system, you can, regardless of how many particles you have, you can sum all the forces and conclude that the total force, external force acting on the system is zero, and therefore the total momentum of the system is conserved. And that's for an arbitrary number of particles. Then we also worked out Newton's second law in polar coordinates. Go and review the expression. I'm not, of course, asking you to remember it. You have the textbook to help you. And remember that certain problems are better solved in polar coordinates, even though the equations are more messy, because it may be that all you need to solve for is some equation for the dependence of the angle as a function of time, while if you did it in Cartesian coordinates, you will have to find the dependence of both x and y from time, and that may be quite a bit more complicated. And that is all for chapter 1. Perhaps I can do this and move things around. So I'm going to pause the recording for a second to fix my writing here. Okay, I fixed it. We have a chapter 1, and now we're moving into chapter 2, what we call the air resistance, which in general could be any fluid. And the idea here is that there is going to be resistance to the motion if our object, the object we're looking at, is moving through a medium. That could be air or water or yogurt or whatever you'd like to drop your things in. And that resistance in general may be fairly complicated, but we can think, well, if that resistance is proportional to, depends on the velocity of our object, which is intuitive, there is more resistance the faster you go. That's part of the reason why cars can, even racing cars can only go that fast. If you try to go faster and faster, the resistance increases. Then you also have slippage for the tires, but that's another issue. Anyway, that force is going to go to 0 if the object is not moving. So we can say if the velocity is small, we can Taylor expand that resistance, and we can start from the first term, which is fluid resistance, where the force, which we call the force of drag, is equal to minus a constant times the velocity. Vectors, so the direction is always opposite. Review the promise that we saw where we have an object falling in with air resistance. So if we assume that that coefficient B is a constant and that's all we have to solve for, then a projectile is going to have an equation of motion that's given by, or two equations of motion rather, x double dot is equal to minus b times x dot, and y double dot is equal to minus b y dot, and then plus or minus depending on how you set up your system of coordinates, m times g. Remember that our book starts with let's see, I think the y-axis pointing downwards, and then halfway through the chapter flips the y-axis pointing it upward, and that may cause some confusion. The thing to keep in mind is that if we have a system of this type, there is going to be a terminal velocity for the object that is, if we let it drop and it drops forever with the air resistance proportional to the velocity will not go to infinity. I just said the acceleration equal to 0, and I can solve for y dot. It's going to be equal to mg divided by b. Pretty easy. Notice that you can have an object moving faster than the terminal velocity as your initial condition. Like you shoot a projectile downwards and you make it go really fast, it will actually slow down to its terminal velocity. If you just drop it, it will accelerate to its terminal velocity. And we worked out the equation for the range of an object and of a projectile with this type of a resistance. And that was kind of rough because it looks something like this. Vy0, so initial velocity in the y direction, plus v terminal divided by vx0 times the range is, well, let me write it all on the left-hand side, plus v terminal times tau. I will remind you what tau is in a moment, times the log of 1 minus r divided by vx0 times tau is equal to 0. And we have to solve for r. which appears inside the logarithm. So this is, oops, sorry about that. This is a pretty challenging equation. But we used clever way to solve it, which I'm going to remind you of in a moment. So what we did in these equations was to define some lower case k is equal to b over m, and tau is 1 over k. So it's m over b. All right. So what you can do here is take the Taylor expansion of the log, expand the logarithm, and that will give you an approximate solution for the range of the projectile. And if we do the Taylor expansion, we obtain that the range is equal to 2vx naught vy naught divided by g minus 2 over 3vx naught times tau times r squared. Which is, wait, when we just solved this for r, the idea there was, let's use the range without air, without drag. And on the right hand side of this equation, that showed you that works pretty well. One thing I wanted to also remind you of is how did we obtain the equation for the range? The idea was the following. Solve for t of x in the x component of the equation of motion, and then we replace it the y component, and then what we have is a function y of r, or y of x. Set y equals 0 and solve for x, which here I called r is in range. And that's in general how you solve this type of problems. So we got our Taylor expansion, and that's pretty much all that I would like you to remember for this chapter. So let's move on to chapter 3. In chapter 3, we talked about conservation of momentum. And the things to remember are, well, conservation of momentum is what makes rocket science. With the right spelling. The two, for all practical purposes, are pretty much the same thing. Of course, if you want to design an actual rocket, you need a little bit more than that. So here the idea is to consider the fuel that's expelled by the rocket and the rocket, that's the thing we want to fly, to be an isolated system. And that will allow you, after some pretty straightforward calculation using just conservation of momentum, to find that the velocity of the rocket minus the initial velocity is equal to the velocity of the ejected fuel times the logarithm of the mass over the initial mass, where the mass is a function of time and the velocity is, of course, a function of time as well. Okay. Then we looked into center of mass, pretty simple concept. It's pretty powerful, but it's a simple definition. It's pretty much the average, the weighted average of the positions of the masses in a system. That is the position of the center of mass, which I indicate with capital R, is 1 over the total mass of the system times the sum over the particles of m, the mass of each particle times the position of each particle. Or if we have continuous rather than discrete system, that's going to be an integral over the volume of R times rho in the R, where rho is the mass density of the system, and it's in general a function of position. And that's the only thing I will want you to remember about center of mass for now. Then we also observe that the total momentum of a system, capital P, is just the mass times R dot, the derivative of the position of the center of mass. This allows us to simplify calculations quite a bit when we are dealing with big discrete systems. The next thing we looked at is angular momentum, which you learned about in physics 1, and maybe I want to give myself a little bit of space to spell out angular momentum here. Almost. And what is important is that the derivative with respect to time of the angular momentum, because, well, let me just write it this way. L dot is equal to R cross F. F is a force, and that's the torque. We're going to use this a lot more later on. We haven't really used it all that much yet. And that's external forces. Really, for a system, internal forces will cancel out, and all that matters is the sum of the external forces. We also reviewed the momentum of inertia. That's an interesting spelling of inertia. Which we indicated with I, which is the sum over all the particles in my system of m, the mass of the particle times r alpha squared, with a similar expression for this continuous rather than discrete system. And again, here is the momentum of inertia takes the place of the mass in equations involving rotational motion. The torque takes the place of the force, and the derivative of the angle takes or the first or second derivative of the angular rotation of the object take the place of the velocity and acceleration. Okay. I hope you're excited about moving on to later chapters in our book that are going to be more fun, I think. But we already did a little bit more work on conservation of energy, which gives us some important results. The first thing we did was to define kinetic energy. Which we indicate with capital letter T. It's one for a single particle. It's 1/2 of mass times velocity squared. And the differential of the kinetic energy is given by the force dot the differential of the displacement. And this is what is called the work kinetic energy theorem. Now, if the force is conservative, we can associate a potential energy to that force. And then we know, you've seen this in a homework problem already, that the work done going from a point to a different point, if the only force acting on the system is conservative, does not depend on the trajectory of the object. So no matter how I get from A to B, if the only force in the system is conservative, all the work done is the difference in potential energy between the point B and the point A. And in our discussion of potential energy, we use the letters U or PE as potential energy. That makes it more visual to say that the total mechanical energy of the system is the sum of the kinetic energy plus the potential energy, or T plus U, which is what we're going to use more often. If there are no other forces acting in the system, this is going to be a constant. A type of force that will stop this from being a constant is friction or air resistance that we have looked at in previous chapters. And the definition of the potential energy, which is a function of position, is minus, important, the sign is important, integral between R0 and R of f of r in the R. This comes from the work kinetic energy theorem pretty much, where, remember, R naught is pretty much arbitrary. So choose it in a way that is convenient. And it's the point where we set our potential energy to 0. And with this definition, the potential energy could be negatives in some place. That's okay. What is the meaning of negative energy? The potential energy is defined up to a constant. So a negative value, it means that the difference between that point and my reference point is negative. There is nothing strange, particularly strange with that. But if there are non-conservative forces, then the variation in total energy is going to be equal to the work of the non-conservative forces. Okay, then we also a reminder, for a force to be conservative, the curl of the force must be equal to 0. Well, really the only way to prove that the force is conservative is to do the integral. Not the only way. The most solid way to do it is to take an integral between points A and B and prove that that integral is 0. Is the same regardless of the trajectory between A and B. Good tool, good mathematical way to confirm that is make sure that the curl of the force is equal to 0. But also keep in mind that the potential energy cannot depend on time. So the force itself may have 0 curl, but it may be, I don't know, increasing in time. Well, then the potential energy is not constant, then the force is not conservative. So always pay attention to that. And the most of the forces we're going to deal with, except for friction and resistance and those sorts of things, are going to be conservative. And the definition of a potential energy is actually pretty useful in other ways. Okay, it's not the potential energy itself that leads to oscillation, but the study of potential energy takes us to the discussion of oscillations. And the reason is that if, let me just do it again. If the potential energy of my system looks something like this, no, U not W, sorry. Then the force that a mass moving in that potential observes is in this direction or in that direction, depending on where the position of my object is. In other words, the force tries to push back the object to the minimum of that potential. And the force is going to be 0 at the minimum. It would also be 0 at the maximum. So if the force is 0, U has a maximum or minimum. It could be a flex point, but now it's let's focus on the maximum minimum for a moment. Okay, so if the point is a minimum, then we have stable equilibrium. If the point is a maximum, we have unstable equilibrium. Unstable equilibrium means what we just saw, that if I push my mass away from that minimum, the mass will try to move close to that, to come back to that minimum again. And when it comes back to that minimum, it will have a certain velocity, so it will actually overshoot the minimum, but then the force changes sign, it will push it back. So what is it going to do? It's going to bounce back and forth, and if there is no dissipation, it's going to bounce back and forth forever. One thing that we can see is that if there is a minimum, the second derivative of the potential energy is positive, and if the second derivative of the potential energy is negative, instead we have a maximum. And again, minimum means stable equilibrium, so second derivative positive means stable equilibrium, second derivative negative means unstable equilibrium, and we don't have any oscillations. Okay, now if we see that, we can say, well, if my object is close to the minimum of the potential energy, I may not quite know what the force, the expression of the force is, but I can say that close to the minimum, if you were kind of drifting into chapter 5, close to the minimum, let me do it this way, sorry. Change of mind. I can Taylor expand the force and stop at the first meaningful term. What does meaningful term means? Does meaningful term mean? It means that we need to get some force and not 0. And what happens if you do the Taylor expansion is that, well, what we do is the Taylor, we can do is the Taylor expansion of the potential. So I'm working one dimension. So that potential is going to be equal to U naught, some value, with the value of the minimum, plus 1/2 second derivative of U divided by x squared calculated at x naught, the position of the minimum, times x squared, or in general, this would be x minus x naught squared, but we pretty much always set x naught equal to 0 for convenience. Okay, so if we do that, then we can also say, well, I can just call that second derivative k, and by setting my x naught equal to 0 for convenience, and doing that calculation, I take the derivative of u to calculate the force. So I have u naught plus 1/2 some constant k times x squared, and the force, which is minus du dx, derivative of u naught is a constant, so that's 0. I get minus kx. And that's the force that we get from mass in spring. Then we can proceed and do some calculations on oscillations. And the way we did it was using complex numbers. And we did quite a bit of work. I'm not going to actually redo the work. I'm going to remind you of the main results. So if our force is equal or approximately equal to minus kx, mass times acceleration is going to be equal to minus kx, or x double dot is going to be equal to minus omega naught square times x. X is going to be proportional to e to the I omega naught times t. Plus or minus, so you have to work out all the algebra and find the constants, and using complex numbers. It took us a little bit of time, but it's a pretty simple idea. Use complex numbers, and that works great for a lot of different things. So you can write the solution as a sine or cosine where you may have an initial phase. And again, I'm not going to write a lot of expressions here. We also look at two-dimensional. So this that result, the cosine of omega 0, from physics 1. Now I noticed that I wrote proportional. There is going to be an amplitude in front, but the amplitude is an arbitrary constant. So for this type of systems, a reminder, the frequency of the oscillation does not depend on the amplitude. Okay, now the next thing we did was to look at two-dimensional oscillations, and we saw Lissajous curves. I'm not going to ask you to plot any of those, and to keep them in mind as something between some good to know and curiosity, but I'm not going to ask you to do any particular work with that. But what we looked at next was damped oscillations, and that's great. So in that case, we found that in general, given the equation x double dot, I'm going to have everything divided by the mass already. 2 beta x dot plus omega naught square x equal to 0, where remember that 2 beta is equal to minus plus b over m, where m is the mass, and the drag force was minus b times v. So minus b times x dot. something happening with my pen here. Okay, so if that's our equation, in general, the solution is going to look like this. X of t is going to be equal to some amplitude. Let me just put it in front, maybe e to the minus beta t times the cosine of omega 1 t minus delta, or I could write this as e to the minus beta t c1 e to the I omega 1 t plus c2 e to the minus I omega 1 t, where omega 1 is equal to omega naught minus beta. Okay, so the possibilities here are for beta to be larger than omega naught, smaller than omega naught, or equal to omega naught. And it's trying to give you all the information in not too much longer. Okay, so what happens here is if you have beta small enough with respect to omega naught, you get damped oscillation that's called underdamped. So you obtain oscillations that look like this. Not this one. This one. With a reducing amplitude. Messed up my plot a little bit. If omega naught is equal to beta, or if omega naught is less than beta, you'll find that the motion is somewhat similar, not identical, but similar, and it will in general look like this. Remember, this may cross 0 once, but it will go exponentially to 0 if you wait long enough. But the shape is going to be, I'm sorry, the equation that tells us what x looks like is going to be different. So the first expression is what we deal with the most, the one with the cosine. But the solutions in these other cases are a little different. They're exponentials, and there is going to be, let's see, I'm just trying to decide how to write it. Oops. Red was not the right answer. If omega naught is equal to beta, this is what's called critically damped. You get a solution that looks like t times e to the beta t. So x of t is going to be equal to some constant e to the minus beta t plus some other constant times t e to the minus beta t. And if omega naught is less than beta, you're going to get that the motion is exponentially decaying. And that's probably not going to fit in here. So let me write it the next line x of t, since it's a little more, the expression is a little more messy, is going to be equal to c1 e to the minus beta minus beta square minus omega naught square. Remember, this is a real number, positive number, times t plus c2, a similar expression, beta plus square root of beta square minus omega naught square times t. The thing to remember is that this looks like uh, an exponential decay in both cases with slightly different shape. Now, the next exciting topic is, well, let's say we are underdamped. The oscillation is decaying exponentially in time. What can we do to keep the oscillation going? Well, apply an oscillatory force. And we discuss why it makes sense to use something like goes like cosine of omega t. If we do that, we find that the amplitude we're going to obtain, let me not jump straight into the amplitude, but we're going to obtain motion that is given by the sum of the homogeneous solution, which is the one we wrote before, e to the minus beta t cosine and so on, plus a particular solution that's going to look like cosine of omega t, where omega is the frequency of the forcing term. Cosine, no, just readable. Let's try again. Cosine of omega t plus or minus, as usual, delta. And this is going to have some constant in front. And the constant, which is, so in this case, it's the way I define it here, it's actually the amplitude. We'll use the letter C in the when we write the solution as exponential. So I don't want to mess up the letters with respect to what we did in class and what the textbook has. So the amplitude is going to be given by F0, that's the forcing term, divided by kind of a bit of a mess, omega naught square minus omega square plus 2, sorry, I'm writing something else. This is all square plus 4 beta square omega square. And this allows us to calculate the position of the resonance or maximum amplitude that we obtain for a specific value of omega, which is omega equal to omega naught square minus 2 beta square, all under square root. And this will give me a maximum amplitude that I can calculate easily from the previous expression. That's F0, so this is the square, divided by 4 beta square times 1 over omega naught square minus beta square. Now you see from these expressions that the resonance is going to be close to omega naught if beta is small, and the amplitude is going to get large if beta is small. Okay, then last thing, we talked a little about Poincare maps or plots or phase diagrams, where the idea is what does my motion really look like? If it's periodic, I'm going to plot the following quantity. I'm going to have x dot and x, and I'm going to plot it at every period. And I'm going to always be in the same point, the same spot. Did I misspell Poincare? Ah, no, it's got an accent, spiriton. If my motion is damped, then every cycle, the amplitude will get smaller, so my line is going to move closer to the origin, go to zero for time going to infinity. And if the system is forced, I'm going to see an initial transient, which is going to be, I don't know, could be all over the place because the frequency of the long-term solution is not the same as the frequency of the initial oscillation, but the long-term solution is going to be just an oscillation, the expression I have above there, cosine of omega t minus delta. So it's again going to be a single point. And I think that's all we did and all we have time for. It's a little more than we have time for, so I went a little long, but I hope this will be useful for your exam. And good luck with the exam. Now I'm going to stop the recording if I can find the button.